Yeah, thanks for having me. I'm actually quite glad to talk here because indeed I have been around the medical imaging community. I was in neuroscience before, but I've never actually attended MICCAI, so it's quite fun to be here for the first time. And yeah, it's not enough. It's not the dinner yet, so I have a bit more time. But great. So actually, that was a great intro. I will repeat a little bit some of the info, but I'll go more quickly over it. So maybe we'll have more time for questions. But basically today I'm going to look at how Causality can really help with building fair medical AI, but also especially what are the limitations and what is the future work that's needed for fair medical AI. So just, very quick, I'm sure everyone is aware of fairness now. It's actually great to see how much this field has evolved. But so here you have chest x-rays of patients who have effusion, which is like water fluid on the lungs. And if you have a young patient...
Jessica?
Yes.
Just a quick. So we only see like the top. Ah, now it's okay. It was just a delay in the rendering. Okay, now we can see. Sorry. Thank you.
Okay. Okay, cool. So yeah, so on the left you have a patient who's younger, and on the right the patient is older, and the model is actually making a mistake for the younger patient. So we ask ourselves whether there is actually a systematic bias in how the model makes its predictions. So this has been now for like a good decade, actually, of a fairly active field. So I'm just going to review some of the fairness definitions and mention which parts of causality are actually relevant for this talk. So when we talk about systematic biases in model outputs, we often talk about fairness and unfairness, and I'm using this definition, which is disparities in model output across demographic groups. So I'm going to be focusing on association bias, which is where you have correlations in your data that basically associate your label and your sensitive attributes. Now, because of those correlations, the model can learn sensitive characteristics, even if they're not trained to, which sometimes we also refer to as incidental learning. And this can lead, like this incidental learning or encoding of the sensitive characteristics in the model representation can lead to also biased predictions. It is necessary, but not a sufficient condition, though. It's not because you have encoding that you do have biased predictions. But we're going to go back to that in a little bit. So in terms of the definitions, like how we actually do this in practice, so we have different fairness criteria that are separated in different families of criteria. So if we take our classic variables, so X the features, Y our labels, A our sensitive attributes, and we're going to focus on predictive models where you have a classifier that from an image predicts your label. And actually here we're going to focus a bit more on disease prediction. So you have three families. You have the independence family, which is that your model prediction should be, or output should be independent of your attributes. Separation is when your model prediction is independent of your attributes given your label. It's quite an intuitive criteria, in especially medical AI, where you have, for example, different prevalences of the disease in subgroups. So let's say, like, older people have more effusion than younger people. Is actually, this is what we see in the data. And so you want to make sure that you have the same error rates rather than just the same overall numbers of predictions, for example. And then you also have sufficiency, where you want to make sure, in this case, that your label is independent of your attribute given your prediction. So this is especially useful when you're predicting risks. Here, and this is after quite a few discussions with doctors and people in the domain, in the medical domain, but I want to caution that a bit, because the choice of a specific metric is a very lengthy discussion. But here, for like simplicity, we're going to focus mostly on separation, and we operationalize that with equalized odds, which is just looking at error rates across the different subgroups. And so for this talk, when I'm going to talk about causality, and I think that was a very useful, contextualization from Ben, that causal inference methods are not necessarily directly applicable to medical imaging, also because they were mostly developed for very low dimensionality data and everything. So it's actually quite complex to put in practice. But the framing is very useful, and especially these graphs. So you've seen a couple already, but just for formalization. So these are causal Bayesian networks. So a Bayesian network is a directed acyclic graph whose nodes are random variables and links express statistical dependencies between them. And so in this case, if you have a set of nodes x1 to xd in the graph, then you can rewrite the joint distribution between x1 and xd and all of the other variables as the product of the probability of, so the distribution of x, like 1x, given its parents. So this is really useful in understanding what is, like, which variables are actually influencing others. And when we extend this to causal Bayesian networks, each link actually expresses a cause. And so we have A causes X. And because there's a direct link here, we are also going to say that A is a direct cause of X. This is going to be important later. And you see this double edged arrow here, where A is correlated with Y. So you can have a correlation by having another random variable, let's say U, that you do not observe, and that's causing both A and Y. But if you don't have access to it, you actually can't, like, there's not much you can do about it. You can also have a selection bias that relates the two. But here, for simplicity, again, I'm going to focus more on, just showing the correlation. So as Ben explained, I don't need to spend much time on this. This is great. We have causal tasks and anti-causal tasks, and for fairness, it definitely matters which task you're dealing with. And in this case, so yeah, I think actually Maggie will talk a bit more about like why it matters in terms of the metrics you would use and in terms of the mitigation strategies you would use. So I'm not going to spoil that. But in this specific talk, we're going to focus more on the anti-causal task. Some of the works also mention the causal task, so like feel free to have a look. But just for this talk, we're going to focus more on the anti-causal tasks. So we predict a disease based on an image. Whether this graph is actually true in a lot of these cases remains an open question, really. But this is going to be our assumption. So I've just mentioned that we're making assumptions. We actually, when we are estimating fairness in medical imaging or any other domain, really, we are making quite a bunch of assumptions. So we are, for example, saying that there is one link here between A and Y. And typically, this is going to be whether this is, oh, this is completely spurious, or, well, maybe it's useful, maybe there's some biological meaning. And the mitigation is either we completely remove it, or we leave it. And this is, yeah, this is really a challenge, because actually, while you do not see, but there might be different effects in that same link. We also measure fairness in distribution, which means that you have your train set, and then you have a test set from that same distribution that you stratify across different subgroups, and this is how you measure fairness. But what happens when you consider distribution shifts and unfairness properties? You also assume that you don't have any other variables in the graph. You also assume that you can measure your attributes and measure your labels without systematic errors, etc., etc., etc. So there are actually quite a few assumptions, which makes it difficult to really operationalize fairness in any meaningful way. So here we're going to focus on the first two assumptions, and I'll show some work that takes steps towards really trying to go into more details and starting to move beyond those assumptions as well. So first, we're going to look at the binary effect of, so this assumption we make about the effect, the association between your attributes and your label to be binary. Like basically it's either spurious or it's causal, like let's say biologically driven. Now, more likely it's actually a mix of both. And so if you have a model that displays unfairness, but you know that there might be a biological cause, how do you know that your model is not amplifying this signal? How do you know really whether the unfairness that you're seeing is due to the biological signal? So we're going to try and answer some of these questions. So whether the model is actually encoding the signal, whether the model is more relying on, the causal or spurious part, although we can't really distinguish that. We can mostly distinguish on whether the model is doing incidental learning and whether it's actually amplifying the causal signal. We're going to see whether the model is stereotyping and whether we can control this association during the learning. And so as Ben mentioned, this actually relates to the literature in, it's typically called, called out in the literature in robustness, which is this shortcut learning. Now, when you look at a causal graph, it can be sometimes difficult to really distinguish between a causal graph that relates to a fairness issue or a causal graph that relates to a robustness issue. And so, yeah, I think here it's actually quite similar in terms of the formalization of the problem. And so this is why the shortcut learning literature is actually quite relevant. So shortcut learning, if we take kind of a high-level definition, is when the model relies on a signal that can vary across environments. In the robustness literature, this is mostly operationalized by looking at the performance of the model on OOD data, so out of distribution data, or looking at worst group performance. It's typically assumed that this correlation is spurious. So the classical example would be like predicting cows from images. And the model actually is doing very well when the cow has a grass background, but the model would make a lot more mistakes if you put a cow on the road. And you want your model to be robust to the backgrounds, so you really want to remove that association. But as I mentioned, in medical imaging, we can have this mix of signal such that if we actually remove the signal, we might end up hurting groups as well. And there's actually some work where they show that if you perform the mitigation, you actually hurt all groups. So we're going to slightly amend the definition of shortcut learning for the purpose of fairness, and we're going to relate encoding, fairness, and shortcut learning. So basically, we make this hypothesis that when a model learns a shortcut, modifying the encoding of the sensitive attribute affects unfairness metrics. So we're going to perform this intervention where we're going to push the model to not encode the sensitive attribute. And we're going to have different scales of that. And to the other extreme where we're going to really push the model to encode the sensitive attribute. Now, if the model is really amplifying the causal signal, then there should be a dependence here. While if there is unfairness that is not related to the encoding, then basically you shouldn't have any variation across this intervention. So in practice, what we do is actually quite simple. It's based on the field of adversarial learning. So you have your network that predicts your output, and you add an extra head that predicts the sensitive characteristics. Now, you have a parameter that modulates the gradients of this additional head. And you can push it in the negative, which is this adversarial learning typically, or to the positive. And we actually try to really span this whole spectrum. And then we test, we evaluate our model basically. We freeze all of the weights, and we measure performance and fairness, but also we measure encoding by, in this case, from the frozen weights, we add an external layer, we add an extra layer that we can train that predicts the characteristics, such that if there is information about the sensitive characteristics, you can reconstruct it from that representation. So this is what it gives, basically, if your model is quite strongly, in this case, shortcutting on age, and if it is not. So yeah, the GIF is a little fast, but basically this is where you will encode, the model encodes age, and this is when it is fair. So here you see that the more it encodes age, the more unfair it is. And if you remove this encoding, then it becomes more fair. So some results. So we've looked at age in chest X-rays because we do believe that, talking with clinicians, again, age is one of these attributes that might be more of a mix, and that maybe it's more difficult to make this a priori ethical decision that you want your model to encode age or not. So we looked at this data set from the NIH, and we're looking at this binary classification of effusion versus no effusion. So these are the distributions of the populations across the ages. So we see that the distributions are quite close, but not exactly overlapping. So we do have a difference in the mean age across the no effusion versus effusion. So we perform our intervention, and we move our little parameters of gradient scaling. And so this is where the model is actually predicting age super strongly. It's encoding age really well to the same level as a model that was trained from scratch to just predict age and not predict the label. And we go all the way to when actually there is absolutely no information, and we've basically permuted the age of all the patients. And the orange dots here, so we have each dot is a model that we've trained with bootstrapping errors, which is quite small, so I'm dropping them further on. But the orange dots is the 0, which means this is the model trained without that extra head. And so what's interesting to look at is the performance versus fairness versus encoding. So encoding is the shade, and when the model encodes less age, it's in the green. When it encodes more, it's in the purple. The orange dots are the 0, so no encode, like no intervention. And then we see that the model, these models are a bit unfair, and they perform quite well. There are some models that are more fair that you could pick, but it will typically come at the cost of some fairness. And so there is a relationship between age, encoding, and fairness, although it's not super striking. So because these distributions are quite close, let's exaggerate that a little bit. So we engineer the shifts in those distributions. We push them further apart by a mean of like around 10 years. And what we see is that, again, we're able to like cover the whole space, but we see that the pattern here is much stronger. So we really have this, this cluster of green dots here that perform really well, like so on the same scale as the original model, but are much fairer than the ones that have been trained on this, engineered bias data. Now we use subsampling, and we actually match the population ages across ages. And again, we can cover the whole space of encoding, but we don't really have a relationship between fairness and encoding here. So basically, this shows that overall, so this is the original data set, and each dot is a model. And so we look at age encoding versus fairness, and we said that if there is a significant correlation, then the model is shortcutting. So here there is a somewhat, there is like, if the threshold is 0.05, then we would say this is significant. So there is definitely some amplification that's happening here. The white dots are the models that are under a certain level of accuracy, and this is user-defined. Now, for the bias data, so the one we re-engineered to be more biased, we have that this correlation is very strong. While for the balanced data, we actually do not have a correlation. Now, this is a bit anecdotal, right? This is only like one data set, one label. We have replicated this for other labels in the same data set, but we also have simulations where we actually really control everything, and the code is available. So what it's something we kind of expected, that, encoding, you can have incidental encoding, and it doesn't mean that you have unfair predictions. But there was still kind of this idea in the literature that encoding could still give you some intuition of how unfair your model is going to be if you were to compare different models. However, what we see here is that this is not the case. So you can have the same level of encoding and models with completely different fairness properties. Now, what we have observed as well is that in this case, subsampling, which uses less data, but subsampling was a very effective mitigation. This is in line with some recent work in machine learning. There are limitations to what can be done with balancing data, but overall, it's actually doing quite well. And even if you have less data, your model is it is doing quite well in terms of like fairness, is more fair, but also it performs at the same level. So this is definitely something that could be tried rather easily if you do have enough data to do that balancing. And in this case, you would want to balance on subgroups of the joint of the attribute and the label. Now, as we mentioned earlier, actually, we know that shortcutting is not the only source of unfairness. So this is not a surprise. But what we see is that as a byproduct of this little dial that we're doing, we do basically generate a bunch of models that have different properties in terms of how much they encode age. And so potentially, even if the model is not necessarily shortcutting on age, but it's unfair, by affecting your age encoding, you could still find models that are performing as well, but have better fairness properties. So here you could be selecting this like purple or this like light green dot here, for example, instead of those orange dots as your model. Although these scores are still probably not something you would want to deploy without further, analysis. And so this actually was, this is data from a dermatology application, so quite similar to the skin lesion that Ben presented earlier, where here we have binarized the problems. We have acne versus not acne, and you see that the difference in the age, like in the age distribution, is very striking. We'll come back to this problem later, so that's why I'm actually explaining this data now. So this method that we refer to as SHORT for shortcut testing, it actually does not depend on a specific fairness or utility metric. The only thing that you would need to consider is that you would want your fairness metric to look at the gaps between groups rather than absolute performance. So something like worst group accuracy is actually not going to do that well, because it has like the effect of overall accuracy on it is actually quite strong, while this is not the case for something like gaps between groups. And you can, here we also looked at performance, actually area under the RC curve. But again, you can think about fairness, about utility metrics rather than pure model performance. So as a byproduct, you do obtain a bunch of different models, and some might have more desirable fairness performance trade-offs or properties. And the method has been validated with simulated data. So when so we have this simulations where we actually have no association between the label and the sensitive attributes, and we make sure that short returns non-significant results, while on the other hand, when there is an association, actually short returns a significant result. Now, this requires training multiple models with different parameter setting for the gradients. So here we trained 25 versions of that model, so 25 settings of that parameter, 5 replicates per setting. Now, this was for a paper. It's not clear that you would need to do that many if you just wanted to have an idea of whether your model is really shortcutting or not. So it's going to depend a bit on how big your model is and how much compute or effort you need to actually train one model. Also, adversarial learning has been quite difficult to put in practice because it's quite tricky to balance the loss, so the actual prediction loss, with your adversarial loss. So we believe that in this work we have found good starting points where you can actually start from this and do a fairly tight search over these hyperparameters. And we have seen that actually this like generalizes across models and data sets. But I believe that, this remains an important point, especially in the case of the dermatology data, where we see that, even though we can cover the whole spectrum from here to here, we still have a bunch, like a big cluster of points at this age encoding. So it's not, super clear that we have really uniformly covered that space really well. Now, of course, we have not talked about downstream harms or health inequity here. And in theory, you can extend this to having multiple attributes by having one head per attribute. But again, this is going to make it really difficult for the convergence of the model and how, these different heads are going to interact with each other. Okay, so I might, if there is any question for this specific part, I don't know if we want to stop here before I go on to the next part, or if I should just go ahead. What do you think?
I think maybe we can take some questions. So there were already a few. You can hear me, right?
Yes.
Yeah, so there were 2 questions online. So the people could just like unmute and maybe turn on their camera and ask the questions. If they don't, I will read them out. I'll just give them a second in case they do one. Yeah.
Yeah, actually, I have a question regarding the classification and prediction. How good should be the performance of the model in the secondary task? For instance, I predict age. How good should it be in terms of metrics? You know what I mean? Because sometimes, for instance, in medical imaging, we are not that good at predicting specific things. For instance, in specific for multiple sclerosis, we are not able to predict a specific score out of just from the image. So how we deal with that?
Sure. Yeah, that's a great question. So here we are actually able to span so let me just show on this. I go back here on this graph, you have 2 lines, 2 dashed line. So here you basically have a model that's been trained from scratch to predict your attribute. And that's going to be your lower bound and, well, or upper bound of performance if you want, but lower error bound on age. And then you have this upper bound here, which is basically you can randomize age across your label. And so that means that there's like literally no association. And so you would kind of want to be able to span this. Now, how close here is actually quite, like you want to make sure that you can reach this line. But if this line is not significant, then probably you're not going to do anything by changing the encoding of age, right? So I would say that if you do have a model that significantly predicts your sensitive attribute, then this is worth considering. If not, let's say you're using a model that's too simple and cannot predict, or your attribute is too complex as a signal, then it's probably not worth trying. I would say, as a side note, that it's quite easy for models to learn attributes, at least from our experience. So even if they can't really learn complex disease signals, they tend to be really good at predicting whether you are male or female, or like different ethnicities, races. Yeah, it's actually sometimes a bit uncanny how well they're doing that.
I think Vibu looks like he's ready to ask a question. Vibu?
Yep, thanks for the talk. So my question is, how do you determine which variables are considered as a source of this unfairness? In our research, age is a contributing factor. For ventricular changes in brain, but here it seems like age is a source of unfairness. So how do you decide?
That's a great question. I think this is more probably on the ethics side and the downstream harms. So you would definitely want to talk with clinicians and think about, like, because I know, and I've worked with electronic health records in the past, and yeah, you just throw all of the metadata in your classifier and like, sure, everything matters. But actually there are some signals that are amplified, and you would want to make sure that they're not amplified in a way that they're not going to make, like, worsen health inequities, for example. So if you have patients showing up with effusion, you want the doctor to actually look at their image before saying that they don't have effusion. So it's still good to measure, even if you think that, there can be this biological link. It's still good to measure whether your model is actually amplifying the signal or not, because it really can happen that your model is amplifying something that is there because it relies on other spurious signals that are correlated with age, right?
Yep, thank you.
All right, thank you. I think these were all questions for now, so we can continue.
Great. So I'll move on to this next part, which is another hypothesis that I've been considering when measuring fairness. And it's a question as how fairness properties are affected by distribution shift. So, this is kind of a classical setup. It's probably a bit exaggerated here, but you have this, source environment, in which you have your typical variables, features, labels, attributes, and we have this extra, it's an indicator variable that tells you that you are in the source environment. So you train a model on this, and you want to deploy it in another target hospital where you also have these variables, but there might be a lot of things that have changed between your source and your target environments. They can be using, if you're looking at scans, they might be using a different machine. The population around the hospital might be different. So you might have people who are more or less healthy. You might have people who have different distributions of sensitive attributes. So all of these can vary. Now, assume that you make your model fair during training. So you see that in your distribution, your model is fair, such that, again, it satisfies this fairness criteria. There is, however, research that shows that these models that are fair in distribution will not be fair out of distribution. So these are mostly, experimental results and conclusions. So we're going to try and really understand why this is happening, but also what to do in which case, which is where causality really matters. So, during the introduction, Ben mentioned a bunch of different shifts that can happen. And there were all of these graphs of potentially you had, a selection shift or change in the covariates or like any type of shift that could happen. But these graphs were mostly assumptions. They're mostly hypotheses of what could happen. And it's actually really hard to test in practice. Now, if we look at the graphs, we do have conditions for the transfer of, across different, environments. If you are interested in transfer of performance, you would want to satisfy this first condition where, V is the set of variables that you include in your model. And so you would want that your label is independent of your environment given your variables. You can also transfer demographic parity with an additional constraint here, and equalize odds as well. But what we don't know typically is what is, if we represent this environment by an indicative variable, how does this actually, beyond assumptions, how does this actually interact with the different variables in your application? So by using some of the causal methods, actually, we've developed some statistical tests that help you. I mean, it's really not causal discovery, but it really helps you try and fill in this graph based on your data. So you need a causal graph of the application. So this gray things, and I'm taking something very simple to illustrate. So you have an anti-causal task, Y causes X. And you want to know what's the effect of the environment on each of those variables. So for the first one, you want to see whether Y is independent of S. Actually quite easy. You take Y in your target environment, in your source environment, and you perform a statistical test. It can be, if Y is a binary classification, then it's actually quite easy. You can even do just a t-test. If you have more dimensions, if it's multi-class, actually, if it's medium size, you can think about just doing multiple t-tests. There's actually evidence that this is enough. And so you can just get this. Do you have an inference of your? So, I mean, to be honest, this should probably be a dashed line, but like here, we're going to assume that your environment causes your Y. Now, once we have this arrow here, we want to test whether there is S is a direct cause of X. So to draw this arrow, we have to test for this. We can't directly do the same thing that we did with Y, because there is this other pass here where it could change the marginal of X, but a direct arrow would actually prevent it if you condition on Y. So here we are using weighting from the propensity score literature, where we actually have, it's classical propensity scores. Here we use overlap weights, but you could be using different things really. So here you basically train a model that predicts the environment from your labels. And then you apply this model to every sample that you want to use in your test. And you re-weight your sample by the output of this model. Now, X here, because we are in medical imaging, is very high dimensionality. So we rely on a summary of the features. So this can actually be any kind of summary you want. But in Lipton et al., when they were doing the label shift detection, they used a black box neural net where they pass the image, they take the prediction out, and this is their summary. So of course, this has limitations, but in our case, that's what we've done. So you would take the prediction to obtain a summary, you take the weights, and then you perform a t-test on that. And this allows you to draw this other arrow where your environment is also influencing your features or not, right? Depending on the outcome of your test. So let's look at some data now. So we take again the dermatology application, so predicting skin diseases from pictures of skin lesions. So this is a multi-class problem. We have 26 skin diseases plus another category that encompasses like hundreds of other possible diseases. And our source is teledermatology clinics from the US. And we have the model, so these are the white dots, where you have, across the whole population, this is how the model performs, split across females and males, and split across ages. And so we see that overall, the model across the different subgroups on the source is actually quite fair. So now we apply this model without any mitigation or anything because it's quite fair. We apply this model to teledermatology clinics in Colombia. And we can see that these are like the blue diamonds here. We see that we have quite different results, especially in terms of age, where the model is really doing worse on the 65 plus. And similarly, we apply the model on skin cancer clinics from Australia. And again, we see that, overall, there is a decrease in performance. But especially the unfairness in age is really striking. And what's quite interesting is this overlap here, where for the 18-29, you have that the source and the target, like the model performance on this group is actually quite good and very similar. So it's not really pointing to the model is completely thrown off and can't predict anything. But it really shows that actually this data set has much more older patients, which drives the decrease in overall performance. So what is happening between those data sets, and what type of mitigation can we put in place to guarantee that you're going to have a fair model on both the source and the target? So let's take our Bayes graph, and let's try to add the indicator variable. So we first test whether the attributes change between the source and the target. So for that, it's the easiest one. There are no parents to A. So we take the distribution of age and sex here that we put together, and we look at whether there is a significant change between the source and the target. And so the source is on the left and the target is this like hashed bar plot on the right. And we actually observe that there is a significant distribution. So now if our graph stays this way, we can actually think about different ways that we can perform a regularization during training, so that we would include our attribute during the training, so that it would basically shield the other variables from the environment indicator. And then we would apply fairness, potentially equalized odds types of regularization. But now let's look at this other variable. Let's look at the labels. And let's test for this. So we have to condition on A in this case. And so we look at the differences in the distributions of Y given A and S. So again, the source is the plain and target is the hashed. And this is for a specific subgroup for illustration, but of course, in the test, you actually, concatenate everything. And what we see is that, again, there is a fairly different distribution of the labels given the sensitive attributes. So we do have to add this arrow. Well, things are becoming much more difficult now. Maybe we can do something, but it's going to be really difficult because changing the labels is quite tricky, but we still have that, X given Y is still like not directly affected by the environment. So maybe if we do a robustness regularizer and a fairness regularizer, maybe we'll actually still manage to get something that is like a model that is fair in the source and target. But we still need to look at X. So in this case, we need to condition on both A and Y. And here, this is just for illustration. This is a summary that I took because you have multiple images, multiple pictures of the same lesion. And in one data set, you have actually more pictures than in another for a group where you have, like for a specific disease and a specific, attribute group. But we actually used a summary of the features as per a neural net that predicts diseases. And we did the reweighted tests. And in this case, we do obtain also a significant effect of the environment on the features. So now things are impossible. In this sense, like, there's actually no intervention you can really do on this set of variables that would give you a model that is fair across distributions, because everything shifts. So we refer to this as like a compound shift, where you have more than one variable that is affected. So you would have multiple types of shift at a time. And these are typically quite hard to deal with. And there are still very few methods. So a lot of the methods actually make assumptions. For example, that you have P of X given Y that is independent of S. And we know that this is not necessarily true. And so we are missing some part of the literature, of the work here to really help in those cases, even though it's not impossible that actually doing a robustness and a fairness regularizer would help decrease the gap, but you wouldn't have any guarantees. So if we think about the whole ML pipeline, and this framework is actually quite nicely explained in Chen et al. 2021, where they think about fairness at every stage of the pipeline. We can really think about this in terms of this as well, on fairness and distribution shift. So it's potentially important to test with labeled or unlabeled. It depends whether what you have access to, but if you do have an anti-causal graph, you will typically need to condition on Y. So it's better to have at least some part of the data that's labeled to really assess the shift complexity rather than making assumptions. Sometimes mitigations are possible, and you have a bunch of work that performs feature selection. It's probably more relevant in tabular data than in medical imaging, but potentially also feature engineering. And actually, if you look into the full paper, we go over graphs for causal and anti-causal and a lot of different cases, and we do some literature review of what would be useful or not as mitigation. And so it's also, when we think about distribution shift, like most of the work on robustness focuses on performance, but it actually doesn't really look at fairness. So when you look at, as soon as you look at out of distribution data, you just look at performance on it, but you don't necessarily look at fairness. And so I think this is important to really consider both. And finally, now we've seen that we don't have methods that can provide models that are robustly fair when the shifts are compound. So in this case, adaptation or using many different environments during training might actually the only solution to us so far. And so again, that's where we would want more work on this. So of course, this work comes with a lot of limitations. It's not because your statistical test for a feature is not significant that it means that this feature is actually invariant across environments. Weighting with, like these propensity scores is very variable. It has a high variance. So you do need to assign a lot of your samples for that. You can do it from the training distribution, so it's not that bad, but still you need enough target data to be able to really perform weighting that makes sense. You do need a causal graph of your application. Now you have other complications where potentially a fairness metric might be relevant only in one environment, but not in the other. So if you worry about different things, there might be a different impact of this. You can't obtain sharp guarantees in the context of compound shifts at the moment. Again, we're talking about fairness in terms of the mathematical operationalization of this, not talking about health equity. This is a much broader discussion. And the method relies on the availability of target data and of demographics. So this remains a quite stringent condition. So in summary, we've looked at these first two assumptions. And we know that work on fairness is already difficult, even when we make those assumptions. But there is much more that we can do to go beyond, and especially there is some interesting work on measurement error in the robustness literature that has not really been transferred to fairness as much. Selection bias is also still something that's not super considered, especially not in compounded with other biases, ignorability. So yeah, there's still a lot of work to do to really make some of that research more applicable, but also in the way that we can really trust that what we're doing is applicable in practice, where we know that these assumptions are really not necessarily satisfied. So I'd like to thank all of my collaborators at Google Research and Google DeepMind, and the organizers for inviting me, and all of you for your attention. I think we have some minutes for questions.